Hi everyone, my name is Hengyuan, and I'm from the EEE department of UCL. And my third year project is about high performance of indium arsenide, gallium arsenide quantum dot laser by using the SLS DFL. So let's start with the introduction part. So what is QD laser? Quantum dot laser has been seen as the next generation technology, which has a huge potential on both military and civilian use. QD tech are fully confined in all three dimensions, which means it's zero dimension. As you can see from the top graph in this section, the QD here is zero dimension, and quantum well QW is two dimension, and the box is three dimension. So let's move on the advantages of QD. QD has a larger gain, a stronger oscillator strength, and a highly stable performance, especially at high temperature. And it has a less dislocation defect than quantum well and box. So next is about silicon substrate. We use silicon as a substrate because it's indirect band gap and the cheap price of making. Integrating the 3 to 5 groups material can bring the high electron mobility and the good optical properties to the system. And the next is about operation system that we used. The operation system we used is MBE system, which can use to grow the QD, which operate at a ultra high vacuum and create a high purity solid source, which achieve a slow growth rate to 0.01 monolayer per second. And there are three chambers in the system. There's a log chamber, preparant chamber, and growth chamber. About the objective sector, the aim of this project is to design a new high-efficient QD laser than before, using some by like reducing the significant defect, such as the striding dislocation (TD) and antiphase domain (APD), that will bring the disadvantages to the laser that will reduce the performance of laser. But in our project, we are mainly focused on get rid of TD. So why we need to get rid of TD? So we need to understand the origin of TD. So TD basically appear as the mismatch between the silicon and 325 groups material as their different lattice constant. Two molecular connect together by a bond, which will create a stress. The stress will accumulate as long as the growth of the QD, and if the strand accumulated to a certain point, it will release and form TDs. And why we need to get rid of TD? So the TD basically is the TD disadvantages. So TD will generate a non-radiative recombination center. This center will trap the carriers. Therefore, the system needs extra carrier, which will increase the threshold current and bring more heat to the system. So how to reduce TD? We are using the dislocation filter layer to get rid of TD. There's mainly 5 different types of DFL. We will find one of the best. White DFL can remove TD. When TD goes through the DFL, it encourages the TD to move and interact with each other. And for some time, they will eliminate when they interact with each other. For the method of this project, the PL measurement, the photoluminescence measurement. So photoluminescence is a light emission after absorbing a photon of any form of matter which has three parts. The first part, absorbing the photon. Second part, the electron will jump from the vacancy band to a conduction band and leaves hole there in the vacancy band. Thirdly, the recombination will happen between the electron and holes, which will generate light. For comparison of the PL spectrum, which can help us to determine which DFL will make QD have the strongest emission. Normally, we are supposed to plot the graph, which is PL against temperature, as you can see from the bottom of the section here. So the DFL that has the highest peak intensity is the DFL that makes the best crystal quality. As we know, TD will create a non-radiative recombination center. This will trap the carriers. which increase the power consumption. And in this case, if there is less TD, there will be much more light emission. Therefore, the intensity will increase as there is less TDs. The result section. So from the right graph, the most important graph in our project is the PL measurement graph. We can clearly see that the indium aluminum acer, gallium acer, SLS, DFL has highest peak intensity when we control the temperature at same level and we change the power supply, which means this DFL can filter out the most of TD in this 5 DFL. However, there are some other criteria that can determine the performance of DFL. The first one is gap between ground to excited state. And the second one is full wave maximum. So let's start with the gap between ground to excited state. From the left graph is the gap measurement. If there's a large gap, which means there is less opportunities for the carrier to escape from the system. So as you can see from this graph, using the indium arsenic, gallium arsenide, QD-DFL can reduce the opportunities for the carrier to escape from the system. And the next one is full wave maximum. Full wave maximum, if there's a narrow full wave maximum, which means the light will generate at a small range of wavelengths and vice versa. We do want our system to generate the light at a small range of wavelengths instead of a large range of wavelengths. So the small full wave maximum is, the better the performance is. So from the middle graph, we can see that the indium aluminum arsenic, gallium arsenide, SLS, DFL, and indium gallium arsenide, SLS, DFL can generate the light at a narrow range of wavelengths, and which means this, when using this DFL, the size of QD are distributed evenly. About conclusion from the result, although there is a lot of criteria from different types of DFL, but the most important criteria is the abilities to filter out TDs. So we are choosing the indium aluminum arsenide, gallium arsenide, SLS, DFL as the final DFL implement to the lasers to improve the performance of lasers. But we do measure the final performance of lasers, as you can see from the top graph in this section. This is the full wave maximum graph, which is quite narrow, which means it generates light at a small range of the wavelengths, which is good. And we can calculate the threshold, which is around 200 by using the reverse extension line. You can see from the middle graph in this section. And from the last graph, we will see the current density increase as the temperature increase, which means the threshold will increase as temperature goes high. So that is the end of my presentation. And I do appreciate to my supervisor Hui Yunliu and Tang Mingzhu for their tremendous help. It's really helpful for me.